We are doing work with Harrison's Energy and homes.co.nz, who's a property website, to model the value of solar potential to every New Zealand's roof. Now, this is a GIS problem. There's an algorithm that determines the received solar radiation based on a component or based on a presentation of surface to the sky anywhere on the planet. And as this little video plays here, you'll see a view of the input receipt across an area. So what we did here is we actually worked with open data sets from government. So one of the great things with New Zealand and our ability to be sort of, I think, at the forefront of this industry is LINZ and other government agencies, local authorities, are really proactive at releasing and enabling key data like photography, like LiDAR, like building footprints to be available and to be put to work. So what we've done is we've done that. So left-hand side is the photography with building footprints on top, machine learnt, okay, automatically defined building outline. So roof position. The right-hand side is the solar surface from LiDAR. So that's the 3D profile of the surface of the Earth. We turn that into a clipped version of solar input and receipt for each and every rooftop. We then worked with Harrison's to determine that against the potential economic value to a household for each and every roof. So in New Zealand, your typical energy bill is about $2,000 to $3,000, depending on your size of your property and your consumption and so forth. A good solar-facing roof in a good part of the country without a lot of shadow, a lot of obstruction, might generate 3/4 of that. So the economics to the household are quite good. If you put a hybrid car in the mix, you might be, on the positive side of the ledger. So there's a lot of really interesting things here in terms of energy consumption, property decision-making, asset value for homeowners to think about. So homes have the reach to a wider audience of homeowners, and Harrison's are wanting to deliver their services and work with customers to enable them to get this advantage. So we'll go one step further. We then look at let's go down to the roof level. So this is just an example, a little clip out of part of Auckland, where we're starting to see, hopefully you can pick up sort of the micro detail. So we can see here, where should that solar panel array be? A 3 kilowatt array is 20 square meters. Okay, so we can work out where exactly, considering obstructions, shadow, the overall geography of the place and sort of longer term shadows. For example, the hills up behind Wellington here do cast a shadow, even though those hills are 3 kilometres away. Okay, so we can understand those patterns. That's where the GIS comes in. That's where the geography is important. And we turn that into where should the panels be placed and what value will they generate? So Harrison's can go confidently to a customer can confidently make a long-term investment. This data is free to consumers. The way the money flows is that when Harrison's receive a lead, we get a small royalty. The customer can have a sensible conversation around the investment they're making. So it's a great use of open data, great use of government expenditure to drive good decision making by residents. That all surfaces up in a nice environment where a customer can see. Here's a couple of examples here. This property here, $912 a year. That's an average sort of property receipt. This one's a slightly better one down below here. So we're trying to take that data right to the consumer. And I want to bring AI back into this mix here, because while this is a really interesting scenario, and there's a bit of AI used throughout this, it's largely a LocationTech problem. This is an example of what's happening behind the scenes with the physics, with the mathematics. There's a whole lot of calculations that go into the determination of solar receipt at a rooftop, including the aspect, the shape, the orientation of the roof, where you are on the planet, the atmospheric conditions. In some cities there's more smog, there's more transmissivity. All those things go into that equation. A 4 kilometre by 4 kilometre tile, this area here, takes 40,000 seconds for us to run on a pretty high grade server, running that physics calculation, because we need to calculate the input every 3 days and then aggregate that to a total year. So we said, let's try and see if we can machine learn that. What's the potential of doing that faster, and therefore doing all of New Zealand faster, right? And updating it faster, getting the data out to residents faster. Well, it's 40,000 times faster. Okay, so we can machine learn that. We can train by example. We can tell our machine learning model, an algorithm, that this right-hand side, which is the solar receipt surface, that's the solar value surface, I'm going to go back. What does that look like based on the physics, based on the science? We're within 5%. So we're within 5% of the actual calculated answer, taking into account a lot of different variables and metrics. Now, with more training, no reason why we shouldn't be able to do that for every location in the country. And similar things. Okay, if there's similar problems that we've got that are very labour-intensive or compute-intensive using geospatial technology, let's consider how we could migrate those to an AI-based approach. I'll leave that with you.